Good morning, my dear kids. In today's class, in the chapter electromagnetic induction, we are going to discuss the numericals on mutual inductance and self-inductance. So these are exclusively the applications of mutual inductance. So what we had the previous class, the discussion about the theoretical aspect of mutual inductance. Now you can see the application part. Later, the wider applications you can see in the AC circuit. Next week, when we go for AC circuit, there in the transformers, we are going to take help of the mutual inductance. Okay, let me start the class. First one, inductors, when two inductors, if they are connected in series, what conditions will arise here? So first we'll take the inductors connected in series. So in series means, again, we can connect in either way, no? Sir, what is there? You mean to say they're connected in series like this? Yes. What is the effective self-inductance? L1 plus L2, we write it. But here, the EMF, the magnetic field, when a current I flows, there'll be magnetic field. We know that the magnetic field produced by a solenoid will also exist on the axis for certain length. And if this L1 is very close to it, the flux generated by solenoid L2 will also link the solenoid L1. And if you send a varying current here, definitely what do we expect? Like the magnetic field produced by this solenoid will also link here, as there's a varying current. Even this will also produce a varying magnetic field that will link the solenoid one. So along with its self-inductance, a mutual inductance also will come. There'll be mutual inductance. So now we are going to discuss if two inductors connected in series and if there is a mutual inductance between them, then what conditions, what will be the effective inductance here? So there's a one solenoid. I'm going to wound a wire. And they're very closely wound. So here to save time, I'm showing that the gap between the turns. Let me send a current I through it. This current I somewhere only in one of the turn will show it here. This is having self-inductance L1, this L2. How the field produced by the first solenoid, use the right hand thumb rule. From the right hand thumb rule, we can show it. There's a field. It will also produce the field in this direction. So this is B1, B2. We know the field here, these are long solenoids. Mu naught Ni will be somewhere in the middle part. No? At the ends, how much it will be? Mu naught Ni by 2. And outside also we have determined. Can you remember? And if they are very close, definitely, if there's a varying current, the magnetic field, this will be variable. A varying magnetic field will link this solenoid 1. The field produced by solenoid 2 will link solenoid 1. And the flux linking the solenoid 1 will change. So there'll be EMF induced. Yes, we should also consider now the mutual inductance effect here. So let the EMF induced in this solenoid be E1. EMF induced in this solenoid be E2. What is E1? We'll write equation. So now I want to replace this with an effective solenoid. Okay, no, this is what is that? L is what we have to calculate that effective inductance here. Now let me define first E1. What is E1 will be? Self-inductance due to varying current, EMF will be induced L di by dt. Then due to mutual inductance, M into EMF induced. There are two things are there. EMF induced due to self-inductance. The magnetic field produced by second solenoid will also link this one. Hope I'm showing the diagram. This will be more than enough. So, or else you get the lines of force like this. Then this particular coil present in the field produced by second coil. If this current I is varying, this B2 will be varying, then flux linking the first solenoid due to field produced by second solenoid will be varying. So there should be some EMF induced. So then is there any mutual inductance? As it is M into this, we are going to write it as di by dt. What is E2? Minus L di by dt. So what is effective EMF? This one, E should be equal to E1 plus E2. I'm replacing these two with an equivalent solenoid. So what is E? Looking at this, what is E? L minus L di by dt. Let me substitute here. Minus L di by dt equal to minus L L1, sorry. Solving this, solving this one. So di by dt, take it out. So we'll end up with L1 plus L2 plus 2M. What is M? That M is a mutual inductance between the coils. So what we should call M? M is a this M depends on what? Again, M depends on what? M again depends on where K is called as coefficient of coupling. K depends upon how that coils are oriented. So again, the K depends upon the orientation of coils. This will be very difficult quantity. Only just we should know the formula. That's what I suggested. Like, sir, regarding K, shall we go for it? It all depends upon the coils, how they get oriented. K, value of K, it will range from 0 to 1. If the flux produced by the second coil doesn't link the first coil, then K will be 0. What all flux produced by the second coil, if it links the first coil, then the K will be 1. So I think the orientation of coils will determine the value of K. This will be very difficult quantity to measure even till date. Just we should have an idea at our level. Let's not go for anything in depth here. So now this M, you substitute here. The effective self-inductance will be now L is equal to so this will be the formula for that. Means, sir, like we'll do one thing, sir. I will increase the distance between them. The value of K will change. Are you getting now? The distance between the coils will matter. Suppose say that if this coil is inside this one, the K will be 1. I think they may trouble you with these questions. I think we have done earlier some problem. What all flux produced by the first coil, if everything links second coil, that is possible only when solenoids are inside each other. Means if this solenoid is inside this one, or I'll take this with a ferrite rod, on that I'll own the two wires in such a way that flux produced by this will totally link the flux. Flux produced by second coil will totally link the first coil. In that case, K will be 1. If you start bringing it outside, now as I keep on increase the distance, the value of K will change. So definitely I can say one thing is like, if second solenoid is present inside, completely inside the first solenoid, Sk will become 1. As you increase the distance, the value of K will decrease. I think you have to remember. So for the given problem, for the given diagram, if the X increases, K decreases. So let me indicate this. This will help you. As X increases, the value of K will decrease. So when do you write L is equal to L1 plus L2? Definitely open the flux produced by this will not link this. In that case, it will be only L1 plus L2. Okay, sir, fine. We didn't understood this particular one. What is this? Like the way you're writing equation. I'm sending a varying current. Then if you send a varying current, this current I will produce a magnetic field, and the magnetic field linking the coil varies. So because of that, we'll get induced EMF. Okay, agreed. Then what about this? When a current, the same current I flows when through second coil, here it will produce a magnetic field in the second coil. This magnetic field will link the first coil, and the flux linking the first coil due to magnetic field B2 will change, and in turn an EMF will be produced. That is due to mutual inductance. This EMF is due to self-inductance. This is due to mutual inductance. Getting the idea now? We'll take the next one. Now look at the direction of current. Here the B bar is in this direction. Field produced by this. The field produced by this will be in this direction. So let the EMF induced E1, the EMF induced here be E2. I want to replace this with an equivalent inductor so that the same EMF will be generated in it. Now, how to write equation? E1 is equal to a varying current flows. So due to self-inductance L1 di by dt. This should be plus M di by dt. Sir, how come you are writing negative? The EMF induced by second coil will oppose the EMF induced due to first coil. The reason for that, to look at the B bar. At this particular point, how the field produced at the location of first coil due to current in second coil will be opposite. So mutual inductance will take the opposite sign here. Similarly, this will be E2 equal to minus L to di by dt. What is the effective EMF? I'll replace these two with an equivalent solenoid. So this will be L1 di by dt. This is equivalent L di by dt. So L is equal to L1 plus L2 minus 2m. Okay, I think the way you connect the self-inductance. So when you connect two solenoids in series, what will be the self-inductance? The self-inductance will vary from L1 plus L2 plus 2m to L1 plus L2 minus 2m. Again, what is m? What is the effective self-inductance will be L1 plus L2 minus 2k. To look at the value, so what is the maximum value? L1 plus L2 plus 2k under root L1 L2. What is the minimum value? L1 plus L2 minus 2k L1 L2. So the value, again, the k depends upon this x. But not only on x, on just on x here. So again, x increases. K decreases. There's a biggest headache with the inductors. Now at some points, I don't want this K. In some applications, I don't want any mutual inductance, this one. In some applications, this is needed. Some applications, this will become unwanted. So that's why dealing with the inductors will become very big headache. Capacitors, okay, will manage, but the inductors not like that. So some applications, I don't want mutual inductance. So what is the case, sir? Like it's a coefficient of coupling, that is. So the symbol for this, we'll put it here. Coefficient of coupling. So what we write is like it's a measure of how much flux linked the one coil due to field produced by the other coil. It's a measure of that one. It is a measure of coil flux linking the coil produced by the other coil. We don't have any depth of analysis, just only some sort of a definition basis. Okay, I think it depends upon orientation, flux leakage, so many things. It's a very complicated topic. Okay, let's not get into more into that one. Here and there, some questions will come, but they're all out of syllabus. Teacher, I don't have any work, so I should create. I should give some difficult question. So what shall I do? I'll just take the electrical engineering books. Plenty of numericals are there. I'll pick up one. I'll dump here. So this is what happening in most of the advanced questions. Now, when they're connected in parallel also will come. I'll write down the formula. The derivation already I derived in the previous in the app. If you want, you can check it, but it's not needed for our JEE advanced syllabus or main syllabus. So if they are connected in parallel, like a mutual inductance, I give one formula. If you are interested, just go through once. It's not compulsory. It's not part of syllabus, that one. So when inductors connected in parallel also, we'll get the effect of mutual inductance. See once, it may not be, it's not a part of syllabus, just like last year I had a time I discussed it. In there in app, I derived it. If you are interested, you can go for it. Okay, now we will go for the application of this one. Okay, before this, I think we will derive the self-inductance of different shaped structures. L of different shaped structures. Different shaped structures, what will be the self-inductance of them? Okay, first this will be a plate. And the diagrams are very poor in books. You find very difficult. Sometimes you'll never understand what, what actually it is. To that extent, the diagrams are there. Okay, these are the two plates. I want the self-inductance of this structure. They're large plates. They're connected by a wire like this. Then I'll make a current I to flow. Let L be the B be the unit per width and L be the length. The separation between them, let be. So I want the self-inductance of this given structure. So these are the plates. There's a plate 1. I'll give a condition L very much greater than B. This is very much greater than it. So there's a plate 1. There's a lower plate 2. So it's a one turn. It's a one turn. Okay, these are the connecting wire. Find the self-inductance of the system. How to find out this one? So what is the only basic formula? What we have is like, you have to take help of the basic formula. What is the basic formula? What it says is like, self-inductance we define as flux linking per unit current. Flux linking the system per unit current flowing in the system. The ratio of that is what self-inductance. So we'll try to find out the flux produced by that. Okay, here I suggest you go for AB. Already we have used symbols. We'll take some other symbols. Let me choose. This is P1, P2, P3, P4. This is P5, P6 not visible, P7, P8. So then what you see is like a stand here. Then you can see like this a current carrying sheets. The upper plate is a one current carrying sheet. The lower plate is another current carrying sheet. So this will become P3, P4. This will become P1, P2. Here you can see current is entering into it. And here you can see that current is coming out. So what is the lambda will define? Current per unit width, I by B, the lambda. Will define here lambda. Go for Ampere's circuit law. The field produced by 3-4 here will be in this direction. And here it will be in this direction. The field produced by P1, P2. And look at this field. So it will get nullified external to the plates. Only in between plates, the field is confined here. The resultant field will get added up. Okay, what is our question? We have to calculate the self-inductance of the system. And we know that this is field produced by P1, P2. Simple. Okay, let me use like P3, P4. So you have to just get only the flux in all these problems. So field produced by P1, P2 is equal to P3, P4. And it is equal to how much? Mu naught lambda by 2. From where this particular formula came? Ampere circuit law. I need not to show this again and again. By this time, you should understand the field produced by a current carrying sheet is given by mu naught lambda by 2. What is lambda? Current per unit width it is. So whatever the net field inside between the plates, point P, I'll write it. The net field at point P is given by P34 plus B P1, P2. Can we calculate the flux? How to calculate flux? Flux linking the gap between the plates. So we'll write it here. Gap between the plates. How much it should be equal to? It should be equal to BP. What shall I write? Area A into L. Don't write this area. Your B bar will be in this direction. So no, sir, not understanding. Not understanding. Okay, come for this. You should have a patience to draw as many as diagrams so that things will get clarity. Here the B bar will be in this direction. I will write here. Now what is this? Net field BP. At least looking at this diagram, can you say anything about the area of this gap? Here, this phase, the B bar will be into the plane. So flux is what? BP into this area. This is AL, no? Okay, what is value of BP? It's equal to mu naught lambda L. What is further? Lambda is I by B. Now, how you define self-inductance? Flux linking to the unit current. Mu naught ALB. So this is the self-inductance of this structure. The first one we are doing. In some applications, so only one turn. Are you seeing that only one turn? Now you may get some doubt, sir. Plate, how come this one turn? I think if you stand here, what do you see? Like you see only one turn here, no? What is the self-inductance of this structure given by this particular formula? We'll do one thing, self-inductance of ring will calculate. Okay, so please note it down. These are very popular. I'm telling this one, in especially advanced, no, they didn't go for very high level. Small ideas is what they're trying to bring in the exam. We know self-inductance, we know mutual inductance, but the small ideas of this kind, definitely little bit you have to put effort here, because we know basic definition. What is the basic definition says? Flux linking the coil to the current in the coil is self-inductance. Getting that calculation of flux is what biggest headache. And now self-inductance of ring will calculate self-inductance of a ring. Okay, let there be a current, high flow through it. Then let N be the number of turns. Then what is the magnetic field at the center of the ring? Is given by mu naught Ni by 2b or 2a. This is a magnetic field. What about the flux linking it? N turns are there, no? So N into b pi a square. Then what is the self-inductance of this ring? It will be flux linking to the current in it. Mu naught N square pi a by 2. N square will come there. If there is a 1 turn, then N will not be there. N equal to, put N equal to 1. The above problem, this problem, the idea is same. Flux linking the coil to the current in the coil. The ratio of that is what? The self-inductance. Next, we'll go for the self-inductance of a coaxial cable. Oh, yeah, take this one. Find the self-inductance per unit length of a coaxial cable. Coaxial cable, I think what all we are using for internet connection, the dish cable, the telephone, for the internet, all this coaxial cable is what we are using. So definitely, I think you must understand what is the, to what extent its use is there for us. I'll construct, I'll show a better diagram. This is a coaxial cable. By chance, if you get an opportunity, just make observation. Because this is thing which you are studying, no? So just a part of cable when it is available. Whenever any cable comes, there must be a cupboard in your home for you where you should collect all these things, cables, different shaped conductors, all that one, and you should make them observation. The nut, bolts. So there's a radius P. This axis. No, get into. So let high be the current flowing through this, and high is the current which will flow on the surface. So I think this is the solid rod it is. There's an outer pipe will be. This will be infinity. It's a long coaxial cable wire. We have to calculate the self-inductance per unit length. So where is I is flowing through this solid rod, solid cylinder of radius A of infinite length, and the current will flow from the outer pipe. So again, it is similar to like the previous one what we discussed. But here cylindrical structure is there. Pipe, okay, all of you? Cylindrical pipe it is. The inside one is a solid cylinder. How the magnetic field will be produced by this. There's a cross-sectional view is what I'm showing it. There's a radius A. How the current here is out of the plane. Go back to Ampere circuit law. What about current everywhere? The current everywhere is into the plane. I'll show only at one point. This is that pipe. How do I expect the field? This is like a long wire only, long wire of radius A. So how the field will be there inside here, the wire, and also in this gap here, there's the air gap. So I'll go for a concentric circles. Few circles, I'll show it. So this is the direction of magnetic field strength. So here it is. So now what is the question that is asked? Self-inductance per unit length is asking. Okay, there's a one diagram, some magnetic field region, where the magnetic field region is there in the gap between. So here, this what you should call. Who will produce this magnetic field? The pipe or the solid cylinder? The solid cylinder. By Ampere circuit law. Will be uniform or non-uniform? Non-uniform magnetic field it is. But how to calculate self-inductance? The two per unit length is asking. So we'll take help of one more diagram. Yeah, no, this will be. Let me assume a strip here. Now look at this strip. Here I assumed a strip. Let's calculate the flux linking this strip. So I think the problem to problem things will change. You have to be very careful. Next, I'll bring another problem where things will be a little bit different for you. Okay, this is the radius R. Thickness dr. Let me assume a L. So how the B bar everywhere here and this will come. This should come like this. First, we'll calculate flux linking this elemental area. So now flux linking. How the B bar? What do you expect B bar? B bar will be according to this. B bar will be everywhere into the plane because the concentric circles. So we are not understanding anything. I think I can't show this more than this one. No? This for that particular strip. What you're seeing this one, no? Is this one available here. And what is the dr? Dr is this one. And this is R. Yeah. Got it now? I think I can't help more than this. There's a maximum help from your teacher. Survey everything. So this won't like this, you have to assume elemental here. So first we'll calculate the flux linking it. B into B into dA, which is equal to L into dr. What is magnetic field? Which is given by mu naught I by 2 pi r due to long wire. This is L into dr. Mu naught IL 2 pi dr by r. Let's go for the limits. Mu naught IL 2 pi. Now what should be the limit? The limit should be from A to B. So flux linking to the current is what? The self-inductance. This is per unit length. Because L is what? One I is missing here. Self-inductance per unit length. Like this, the different structures will have the different types of conditions. You should be alert. Because they don't tell like where is the flux, where you have to calculate. Just says like a self-inductance per unit length of coaxial cable. We should assume how the field will be. Then how that current will produce magnetic field, then what is the elemental area, what is the structure that we are supposed to assume. Don't expect everything in the numerical. This I should not be there, no? Yeah, this I should not be there. Yeah, okay, yeah. Fine, huh? So we are we'll take the rectangular cross-section toroid. Find the self-inductance of rectangular cross-sectional toroid. We'll try to draw a diagram. Not correct. I'll give the better diagram. Okay, there's a rectangular cross-sectional toroid of height h, shaped like this. Very important and can be asked such things in exam. So toroid, can you remember Ampere's circuit law? We have discussed toroid. There the cross section was circular. Here the cross section is a rectangular. This will be rectangular. So the small gap will be there here to make the diagram. I'm making things visible. So here these are the turns. Okay, no. This side view. Of inner radius A, outer radius B, and this is that yellow color one. Okay, carry on. A small gap, we have to show it. Hope if you can remember, directly let n be the number of turns. Go back to Ampere's circuit law and get that formula for magnetic field inside this toroid. Once you know magnetic field, then we can go for self-inductance like previous problem. Let n be the number of turns, inner radii A, outer radii B. Or the magnetic lines of force. So let's assume that current here. Current here. So let me send a current I here. A current I will flow. So it will produce a magnetic field. This magnetic field lines, I'll show it, circular one. I can show only 2 or 3 lines. Small narrow gap it is. Very small narrow gap it is. In fact, should not also be there to make you explain what I just brought it here. I think, okay, the gap should not be. Let's remove gap. Again, you'll start thinking some other way. Yeah, carry on now. So the lines of force will be in this direction. What is the expression for B bar? First of all, B bar. Anybody? We discussed, no, the value. B bar at a distance R. So what I do is like I'm going to assume a DL here. B bar dot DL equal to mu naught N into I, no? Why N into I? So these many terms, 1, 2, 3, 4, 5. Here is what the Amperian loop is assumed. So how many turns are enclosed? 1, 2, 3, 4, 5, 6, 7, 8. So N I's are enclosed here. So this will become B bar into DL mu naught Ni. 2 pi R mu naught Ni. Look at the magnetic field. In fact, the magnetic field is variable here. If B is very much greater than A, then it will remain constant. Okay, no, the B is variable here. So I am going to assume now here a strip. Height of the strip already given H. Let it be dr. So what is the flux linking this strip is what? We'll calculate here. So d phi is equal to B into dA. B into what is dA? H into dr. B is equal to mu naught Ni 2 pi r H dr. Mu naught NH I 2 pi dr by r. Just from college, a call is there. Meanwhile, you finish off. I'll attend that call. What should be the limit? Limit should be from A to B. So solving this, flux equal to mu naught NH by 2 pi I log of B by A, self-inductance. Widely used in plenty of applications. You may encounter any of structure, like how to find out the resistance of various shaped structures, how to calculate the capacitance of various structures. Like that also, self-inductance of different current carrying structures can be asked for you in exam. Now we'll go back to, so this is about, we'll go to the some numericals on mutual inductance. Once again, we'll go back. So there are plenty of different ideas are there, which I wanted to share. This will be very useful for you in exam. What I'm going to discuss, the mutual inductance ideas. Let's go for the application. So the first one, we'll start. So I'll begin with a very simple. Let there be a long wire. Let this carry a current, which is I naught T. And let there be a conducting loop. Which is having a resistance R. Lambda be the resistance per unit length. So which is at a distance A, let this be, side length is L. What is EMF induced? What is the expression for current? What is lambda? Lambda is the resistance per unit length of the loop. Same, this problem only will modify things. So I want expression for induced current in the loop here. Find what to do, how to find out. We know I'm going to go for take help of mutual inductance. So there'll be EMF induced. If a varying current flows in this structure, it's a long wire. How do it will produce EMF induction? I'll calculate mutual inductance. With the help of mutual inductance, I can go for how to calculate mutual inductance. So first, what we do is like let's calculate the flux linking this structure. Side length of this is L. So what is the flux linking that? D phi equal to B into dA, which is equal to B into L into dx. What is B equal to? Mu naught I due to long y. L into dx. So further, this is mu naught I L 2 pi dx by x. The limit will be A to A plus L. One plus L by A. Okay, there's a flux linking. Mutual inductance, how you define flux linking the coil to the current in the coil. Mu naught L 2 pi log of 1 plus L by A. Okay, this is the mutual inductance. Now, what was the question asked? We have to calculate the induced current. So what is the formula for induced current in the loop? The induced current in the loop should be equal to M into di by dt. What is M? M is a mutual inductance. Di by dt is the current in the wire, rate of change of current in the wire. According to this, it should be equal to M is how much? Mu naught L 2 pi log of 1 plus L by di by dt is I naught. There's the EMF inducer. So what is the current in the loop? Current in the loop equal to E loop by lambda into 4L, resistance of the loop. Mu naught I naught log of how that induced current will flow by Lenz's law. It has to be in this direction. Getting the idea? The idea of mutual inductance. See why I am asking you to think like this. I will slowly introduce one by one. I'll slowly introduce all the things one by one. It'll be this one problem is sufficient to understand things which I'm going to explain now. Okay, everyone fine. So there is some sort of EMF is there, no? So what we can replace that loop by a source E loop and also the resistance. So what is the equivalent circuit of this will be? The equivalent circuit. Can we adjust here? The equivalent circuit, it will be, there's a I. So the whole circuit, actually we are supposed to replace with a this will be better picture. A student has to go to this level. There is some sort of sources, EMF is generated, a cell and a resistor. Agreed? This is our electronic, like a electrical way of thinking. This is I loop. Just make observation. I'll make some small changes here. And now, shall we bring one capacitor along with the rest? I'll slide down. Now, instead of this, okay, we'll go for, there's a wire. The loop itself contains one resistor and one capacitor. Side length, let it be L. Then a varying current, I'll send it. I want steady state charge across the capacitor. It's a loop. Hope everyone is able to understand. It's a loop, and the resistance of the loop we are showing that it, let it be R. So I'll write it here. So let it be at a distance. L will take it so that it will become very simple expression for us. I want steady state charge across capacitor. First, we should calculate EMF induced in the loop. So whose help we should take? This particular formula, EMF induced in the loop. M di by dt. I think this will become log 2. EMF induced in the loop should be equal to log 2. So what is the equivalent circuit will be? The equivalent circuit we should go for, I'll do one thing, a loop having resistor, a loop of side length. Is placed nearby a long wire find steady state charge across capacitor. Okay, this is a question that is asked here. First, we will go for equivalent diagram. The equivalent diagram, what it says, there should be a cell. Can we go for the EMF induced across the cell? So there should be the cell, there should be the resistance, there should be capacitance. So from where this EMF we have brought it, so expression for EMF should be equal to M di by dt. This should be equal to mu naught L 2 pi. Yeah, I think we can see completely. Log 2 di by dt is I naught. Hope everyone is able to understand here. Sir, how come log 2? Here length A is equal to L, no? Because of A equal to L, what we are getting is mu naught L by 2 pi, log 2 will get it. And di by dt is what? I naught. Now these are very important, especially for exam purpose. A student must know how to take that help of mutual inductance. So I got EMF induced. Then at steady state, Q infinity should be equal to E loop into C. Okay. So this is a steady state charge. You should not get scared. Sir, so many things. Let it be. some mutual inductance is there. So there'll be EMF induced in cell. So how you determine the polarity of cell? I think by Lenz's law. Flux negative, negative flux increases, d∅dt negative, EMF induced positive. So therefore the polarity of cell is given in this way. Sir, I want the current in the loop at any time t. I think we should go for RC circuit, concept of RC circuit. What will be the current in this? At steady state should be zero, no? Please don't get confused here. If it were only resistance, okay. Because of capacitor, now you bring just like that EMF induced is a cell, that's all. Again, it's a pure RC circuit problem with a cell. From where that EMF of cell? Due to mutual inductance. Able to understand now? There's a very basic problem. This can be asked in different way here. Anybody having doubts, you can clarify. Okay, let me introduce inductor here, then we'll see. That particular loop will have inductance. If you take any loop, it will have inductance. Self-inductance of the loop, let it be L, and R be the resistance of the loop. How do we manage this one? This loop will have self-inductance. Now total EMF generated in the loop. Okay, now we'll place it. A loop, a square loop of resistance R and self-inductance L is placed nearby a long wire as shown. Find net EMF induced in the loop. Find the net EMF induced in the loop. No. There'll be EMF induced in the loop due to mutual inductance. There'll be EMF will be induced in the loop due to mutual inductance. That we know already better. So what to do that inductor? Due to inductance also there'll be EMF will be induced, no? Due to inductance also, there'll be EMF induced. First, we'll calculate EMF due to mutual inductance. EM, I'll write it. What is that EM? Should be equal to mu naught L 2 pi. Again, the mu naught L 2 pi log 2. Okay, the formula, okay, mu naught L 2 pi log 2. I think better remember, it's going to help you a lot. This is the EMF induced due to mutual inductance. Next, EMF induced due to self-inductance. That should be equal to L di1 by dt. What is I1? What is I? I is the current flowing in the loop. So we are not understanding anything. It's definitely nobody will understand unless you don't draw a diagram. Shall we replace this everything here like a cell? Put a cell. This is EM, a resistor. Then the coil, self-inductance of coil, bring it here. Then a current will flow high. What is the equations you are going to write now? How you are going to write equation? I'll come to this later on. Let's stick on to RL circuit. Just now, see, like I hope everyone, there's a resistor and capacitor, EMF is produced, no? So what you're going to do, you're going to bring a cell. Then you're going to write expression. Similarly, the same thing here also. Nothing big deal here. So what is the equation? EM minus IR minus L di by dt equal to 0. Net EMF induced means L di by dt. L di by dt is also some sort of EMF, no? If you're treating circuit element, you're treating like a drop. But you can treat it like a EMF also. Net EMF means the difference of these two. Able to understand? No? So I suggest you, like, this is due to self-inductance. This is due to mutual inductance. Just bring that EMF due to mutual inductance, bring that cell, then treat like RL circuit and work out. So let me just write comment. This is due to mutual inductance. Self-induct. This is mutual inductance between wire and loop. This is only due to self-inductance of loop. So nearby, if you get anything, nearby, if you get anything, like a current carrying wire, no? So due to that, what will happen? There'll be current starts flowing it here. If a constant current flows, I think no question of any mutual inductance. Am I right? Let me go for still more very generalized discussion. There are two loops are there. This having a cell E1, resistor R1, there's a capacitance C1. There's another loop capacitor C2, resistor R2, this is cell E2. I think this will be very interesting for you. There's a mutual inductance. The mutual inductance, we just show it arrow like this, means there's a mutual inductance between them. And mutual inductance is such that it will be EMF produced. Due to that, there'll be EMF produced, and each loop will have its own self-inductance. Why? Because any current carrying loop should have self-inductance. Let L1, L2 be self-inductance, let M be the mutual inductance. Then can we calculate the expression for current in the first loop? Let I1 be the, or in general, let I1 be the current flowing here. Let I2 be the current flowing in this loop. Net EMF means the total resultant EMF, EM minus EL. I'll write it. You wanted that. Okay. I wrote this equation treating inductor as a circuit element, but you can treat it like a cell also. Look for this. Let M be the mutual inductance.
Sir, in the previous problem, in EN, I0 is missing.
I'm not understanding. Like
in EN, sir, we have to write I0 also. Mu not L I0.
Here I0. Should not be there. Should not be there. Should not be there. Should not be there. Yeah. Then go back. Should not be there. No mutual inductance.
Sir, EMF also.
M is mu naught L by 2 pi.
Line 2 into.
Sir, EMF of loop, sir. Not current of loop.
Yeah, EMF of the loop, no?
Yes, sir.
L di by. Okay, fine. I0 will be there, yeah. Yeah, okay, agree. Only M I wrote into M into di by dt, that will become I0. Okay, yeah, fine. Let's take this one. Let M be the mutual inductance. M12 is equal to M21. They're assumed like this. Let I1, I2 be the current flowing. So let's write the KVL equation for this. So along with this cell, there's also cell, resistor, capacitor, and inductance also there. Now there'll be mutual inductance by this. The flux linking by it such that we have to write equation. There's a general discussion. What is M? M is a mutual inductance. Means a current flowing here will produce a flux. The current flowing here, due to that, a magnetic field will be generated. This magnetic field will generate a flux. And there's a varying current. So definitely what do you expect here? A varying magnetic flux link. So there'll be mutual inductance between them. Let M be the mutual inductance. Sir, how much it is, we don't know. I hope are you able to understand now? Now we are going for gen. And what is L1, L2? Because any current carrying structure will have self-inductance, let that be L1. This is the best, I think I'm giving the use that one. Sir, why current is variable? Who will answer? If I switch on the cells, what do you expect current? Transient currents will flow, no? Then what do you expect? Okay, this cell only will influence the flow of current. If the two circuits are nearby, the current flowing in this circuit, a varying current flowing in this circuit will have influence on other things. Just go to the electronic circuit, television. We do have so many blocks, no circuit blocks. A varying current will be flowing in them. In fan, electrical equipment. I think one block of circuit will disturb another 10 blocks of circuit. Just imagine for 2 blocks of circuit. I'm calling this a block 1, block 2. This itself we are struggling. 10, 15 blocks means on the one block, suppose 15 blocks are there. Blocks means, so okay, are able to understand in the total circuit, I'm breaking up that into loops, that one. So there's a block 1, block 2, like that 15, 20 blocks will be there. On the block 1, there'll be impact of another 14 blocks. how engineer will cope up. Yeah, that's what I'm telling this one. It's not that easy in designing of circuits or doing research analysis. Production is okay, fine, but the designing part is so complicated. Even the circuits also, it will be very challenging for you to bring, keeping all this in mind, and still the performance to be at best level. My experience, the design of one circuit in the PCB board, it takes 6 months. We have to test. See, designing will come again, checking all the parameters one by one, nullifying it, everything, and generating final output. Again, the error analysis. It takes 6 months. Just a small, means a small circuit in the watch. To generate that, it takes 6 months with minimum errors. Just imagine television. Just imagine laptop. So is it really that easy, all these things? Somebody might tell, okay, BTech, what is there are 4 years, happily you can enjoy and study like Happy Days movie. So I let me not speak more than this. Huh? Let's come to the problem. Okay, these are the cells. I'll switch on both the cells. At t equals 0. Both the cells are switched on. What are L1, L2? Switched on. Let L1 and L2 be the self-inductance of the coils. Let's see that what all we can write equation. E1, we are very familiar with few things. What all we are very familiar, we'll write down first, and there'll be also self-inductance, L di1 by dt. Then mutual inductance, M into di2 by dt equals 0. This is for loop 1. So from where you brought this? This will be due to impact of second loop. In second loop, a varying current is flowing. A varying current here will produce EMF induced, and that is equal to M into di2 by dt. Sir, how you can say this should be positive or negative? Anybody answers? It all depends upon the direction of this cell. Am I right? It can be positive or negative. Am I right? So some books, they put this as plus or minus. Okay, fine, justify, nothing wrong. But this you cannot write plus or minus here. You know, this is a circuit. Am I right? For these things, the sign is specific here. This can be plus or minus. It all depends upon how the current, if current flows here, the magnetic field is into this plane. If a current flows in there, the magnetic field will be out of the plane. So this can be plus or minus here. Got it? No? Similarly for second loop. E2 minus Q2 C2 minus L2 di2 by dt minus M di1 by dt. Getting the some very general idea. Again, sir, this M depends on what? M depends upon how close they are, and the sign also depends upon like how the current here will link this.
Sir.
Yeah.
Sir, if I1 decreases, then should we write di1 by dt as negative, sir?
Yeah, that's all. See, this part is already we know. This is what mutual inductance. I introduced new one. You remove this. Don't you know these things all? RL circuit. Apply RL
Yes, sir.
circuit. There's a mutual inductance additional thing we have brought in. That's all. Try to separate things here. Don't mess up everything here.
Okay, sir.
Okay, these are the where A, B very much greater than a current of variable current. Let me send it. Let R be the resistance of this. This resistance, I'll bring it here. No. The diagram shows concentric loops A and B. With current in inner loop varies as I equal to 2t square. Find the current through capacitor at steady state. So one instruction, neglect self-inductance of larger loop. Now carry on. This will call loop 1. There's a loop 1. There's a loop 2. Will there be any EMF induced in the loop 2 due to varying current in the first loop? Look at that conditions given, B very much greater than A. Now first, we should calculate the mutual inductance between them. How to calculate mutual inductance? I will jump to the let's get into the discussion here. So there's the inner loop. There's the outer loop. The resistors, capacitors I'll bring later on. Let's send a current here, say some high that one. Will it produce any magnetic field at the center of the loop? There's a loop 1. There's a loop 2. So what is the magnetic field produced at the center of loop? Mu naught I by 2b. Flux linking the loop. B2, I'll write it better. We'll use symbol. I2. Yeah. Flux linking the inner loop should be equal to B2 into pi a square. Mu naught I2 by 2b pi a square. Then how you define mutual inductance? Mutual flux linking the inner loop due to current in the outer loop. That should be equal to mu naught pi a square by 2b. Now one question like, okay, sir, what is this magnetic field? Can you tell me once? The field strength at the center, but the magnetic field at different points will be different. How come you're assuming the magnetic field everywhere inside the loop to be constant? Because what you found out, this equation is at the center, magnetic field at the center of the loop, mu naught I2 by 2b. But will it be magnetic field everywhere same? Look at this condition given. The size of inner loop, the radius of that so small that what is the field strength at the center, that will be same everywhere inside the loop, inside the inner loop. I think this assumption is very important. What you calculate magnetic field strength at the center of the loop, that is going to be there, same value everywhere inside the inner loop. So the EMF induced. Okay, now we got mutual inductance. So can we calculate EMF induced in the outer loop? Do we know mutual inductance? It is mu naught di1 by dt, di1 by dt. So what is I1? So this should be equal to 4t. Okay, now we are in a better position. So there will be a cell, capacitor, there's a resistor. Very calculatively we have to work out here. And the question, so this E2 we know it. So now he's asking find the current. Okay, let's write the equation. Q minus Q, and the current I will flow. These are the polarities. So the equations will be plus C2 this, sorry, high. So what is the problem? I think this everything is a big constant. So I'll bring K. Every time writing this will be a big headache. We wanted expression for current here, no? Shall we differentiate here? Again, once again, this will be K minus 1 by C. I think this can be solved very easily. At t equals 0, what was the current? 0. At any time t, let I be the current. I think, okay, we are in far better position. We can work out now. 0 to I. What can be? Kc. Now look at this. It's asking steady state current. What shall we do at t equal to infinity? We had some basic idea. What is that? A steady state capacitor open circuit current will be 0. So one option will be there, 0, so that you can pick up and go wrong. Look at the cell. If the EMF of cell varies with the time, then the steady state current will not be 0. There'll be continuously there'll be flow of current. Just to make students to go wrong, because maximum we did so many problems at steady state, current through the capacitor will be 0. So maximum students open options will be 0 there, they'll pick up 0, that's all. They don't think anything. So we'll write it here. Steady state current. You do get plenty of questions based on this mutual inductance. This will be our answer. The more troublesome, this is what actually, because the current flowing here, how to calculate the flux linking the outer loop, I think you'll land in a big trouble. Since the idea of mutual inductance, you bring it. Let's assume that a current flowing in the outer loop, and then we'll calculate flux linking the inner loop, then flux linking the inner loop to the current in outer loop will give mutual inductance. Then we are proceeding here. But students, they don't think this one. They directly want to find out how to calculate that one. Not possible. Same thing here only. If I send a current I in this, what is the EMF induced in this wire? Can we find out? Yes, we can find out. But what is the problem? Can we find out the flux linking the wire due to current in this? Mathematically, we cannot find out. So what shall we do? Let's assume that a current flowing in this will calculate flux linking this, will calculate the mutual inductance to trouble you. In most of the numericals, if a current flowing in one loop, flux linking other loop, you can find out. But in either way, not possible. It's like a current flowing in long wire, due to current flowing in long wire, flux linking the loop, we can find out. If a current flows in this wire loop, then what is the flux linking the wire, we cannot find out. Don't say it will not exist. We don't have mass to find out. Let's come to the problem. Yeah, it's here, we are here. Let's have one more. So let's take a situation. So no resistance of circuit is negligible. Okay, this cell is ideal. Resistance of circuit is negligible. Okay, now we'll at t equals 0, the switch is closed. I want the expression for find I of t. What to do now? If there were any resistor, we would have written that equation very easily. But look at here. Let's write loop equation. We'll see where we'll end up. Let's see. Minus L di by dt at an instant of time. There's the only equation what we can write. If there were any resistor, I would have brought that IR drop. Got it now? There's no resistor, so no IR drop here. So this will become E equal to L. Look at the current now. It will increase linearly. Let's not see whatever happens. We have to stick on to this. Our KVL is the best friend will help you. I think the whole concept I just took help of KVL. You see almost all numericals. I didn't divert it. I didn't dump anything. Okay, like this only you think it. This is a method. Okay, this idea. Some books they rubbed forcibly the ideas. No, you write it like this. No, we'll take help of KVL. Whatever the circuit, no, mutual inductance, self-inductance, resistor, capacitor, cell, whoever may come, we just take help of KVL. There's a universal why it's a law, no, it will be applicable in all the situations. Let's stick on to that KVL. So I think the self-inductance we started, I took help of KVL. Mutual inductance also, I asked you to take help of KVL. What is the mutual inductance? Due to mutual inductance, then a source will be generated in a circuit. So give that polarity for that source and carry on the problem as usual KVL. Okay, so I think you should be ready with the questions of this kind. So now, what about the current in this? How do current and energy across the coil? It will continuously, current will increase linearly with the time. What about energy across the coil? I think high square, it will be parabolic. So you may expect a graph of this kind. One more small problem. We'll give one resistor here. Okay, these are the two switches are there. No. Okay, these are the two switches are there. Now what we are going to do is like a steady state. I'm going to open these switches. What will be the reading of ammeter? So let me bring one ammeter here. And I'll bring one more ammeter here. Ammeter X, ammeter Y. So at T equals 0, at steady state, the switches S1 and S2 are opened. Just after opening, find the reading of emitters X and Y. This is another way of asking some questions. Just like we are going to learn regarding the inductors. Carry on now. Just after opening the switches, find the reading of emitters. There's one more very important part of the inductors is what, as a teacher, I should conclude here. So at steady state, there'll be a charge here, no? Q infinity, Q infinity. And there will be a flow of current. Okay, that I'll call I infinity. That we have to later on, we have to calculate. So till here, I'm very much sure about, okay, like this, there'll be a flow of current. The moment I open switch, so when we open switch, then what conditions will arise? How the current through the emitters will flow? Will they flow in the same direction? Okay, the switches are open. No. What this capacitor will do? There won't be EMF due to cell, no? So there won't be influence of this cell on either the capacitor or inductor. Agree? The first part. Then the capacitor is having a loop. It will try to discharge here. Then there will be a current through this one. How the current will flow in this direction. Okay, this is what IC will say. Now, what about here now? Anybody? Yes, we know from the self-inductance, there won't be EMF to support this current. The flux across this coil starts collapsing, then there'll be induced current, and the induced current will flow in the direction of initial steady state current. No, so there will be an high steady state. IL will write it. So what is that IL? IL should be called I infinity only. Same direction, but here it will be different. During charging, the current was flowing like this. Now the discharging, it flow in opposite direction. Am I right? Because this is a positive plate. So it starts discharging, so the current will flow like this. Whereas here, the current will flow in the direction of the earlier steady state current. This is something I wanted to. So what is IC? Can you find out? Yes. For that, you should know Q infinity, other things. So how to calculate I infinity? You go for, this will be a short circuit. This will be open circuit. Then work out from current LCT topic. I think, okay, these two are parallel. These two are parallel, and this will be connected to this. Redraw the circuit properly. Work out and calculate the I infinity. That only is what IL. How to calculate IC? IC is what? Q infinity by lambda 2R. Okay, I think the direction of current here will not be like this. In fact, will be like this. When charging, the current was flowing here in this direction. When you open the switch, the current will flow in opposite direction across this emitter. Across this emitter, why there won't be problem? You see this. It will continue to flow in same direction. The reason for that, according to the like a Lenz's law, the direction of induced current is such that it should oppose its own cause. The steady state current start decreasing. So therefore, the inductor will push the current in same direction. So what are the type of questions? Instead of asking here, find the reading of emitter or find the direction of current through the emitters. Means earlier it was flowing from A to B. Now how it will flow? It will flow from B to A. Now it will flow from P to Q. And this is a very popular, so just do think on this one. Yeah, I'll end up the class. Okay, kids, we had a good discussion about the self-inductance and mutual inductance application problems. So just do think on them and try to work out few more better problems so that you'll be in a like a excellent position to deal with any problems related to these particular topics here. So let me end up the class.